Hello, welcome to another video on differential equations, and this time it will be about differential equations and modeling. In the previous video, we have taken a look at differential equations, and that was mostly from a mathematical perspective. So we had a few examples for differential equations and wrote down their solutions. And we already got a feeling that differential equations can be quite complicated. Now, much insight about differential equations actually can be drawn from applications. For example, if you've got differential equations that relate to phenomena in physics or biology, then typically the knowledge that you have about the physical phenomena or the situation in biology can help you already to get an idea of how the differential equation behaves from a mathematical perspective. So for that reason, we talk about differential equations in modeling. We will take a look at a few examples. Some of these examples are quite simple from a mathematical point of view, but I believe it will be helpful to just discuss how these relate to mathematical modeling. Last but not least, if somewhere on your hard drive or somewhere in your basement you've got an old and forgotten Euler method lying around, maybe it's a computer code that you've written for one of your calculus classes, then now it is a really good time actually to dig out that code and get in touch with it again, because it might be helpful to you just to use that piece of code to illustrate some of the methods that we're going to discuss. Let's start with our first example. Now, suppose you are a recreational blacksmith and you own a forge, and you also have a huge lake right next to the forge. And so what you do in your free time is you heat a piece of fire, you make it really hot, and then you decide just to drop it into the lake. Now, what you're going to observe is that the piece of iron is slowly going to cool down, and at the end it's probably going to reach the temperature of the lake. Now let's assume the lake is really huge, so practically the temperature of the lake remains constant, just to simplify this model a bit. And what you're interested in is to describe the temperature of the piece of iron over time. You would like to have an idea how this piece of iron cools down, and initially it will have a really hot temperature, and then you would like to describe what is the temperature after 2 seconds, after 1 minute, after 1 hour. So we will describe the temperature of the piece of iron by a function, C of t. T in this case, of course, is a time variable. So the lake, we assume, has a constant temperature, which we call Cl. And right at the beginning, the hot piece of iron has an initial temperature, C0. Now, we might not know the temperature of the piece of iron at any time right from the get-go, but what we might know from physics is that the rate of heat loss of the piece of iron is proportional to the temperature difference at any time. So at any time t, the rate of heat loss is proportional to C of t minus Cl, the temperature difference of the piece of iron and the lake. We would like to describe the temperature Ct by a differential equation. Now, C prime of t, the rate is the rate of heat loss at time t. It's the derivative of the temperature function at time t. And okay, we know it's proportional to the temperature difference of the piece of iron in the lake. So that is why we've got this vector C of t minus Cl. And okay, it's proportional, so we have some proportionality constant alpha. The precise value of this proportionality constant alpha will depend on specific material properties of the iron and the lake and the water in particular. The slope of the temperature function C at any time t is going downward, so that's why we've got a minus sign here. So the entire differential equation reads C prime of t is equal to minus alpha times C of t minus CL. And if we now simplify this a bit, then we can rewrite the right-hand side as minus alpha C of t plus alpha CL. And last but not least, the initial condition of our model is C at 0 is equal to C naught. And for this, we can just use the theory that has been developed in the previous video. And just applying the theory, what we get is C of t as an explicit formula, namely C of t is minus CL times exponential of minus alpha t minus 1 plus C naught times exponential of minus alpha t. Now, if we simplify this a bit, we can also write this down as C naught minus CL multiplied by exponential of minus alpha t plus CL, and a graph of C of t is given here in the bottom of the slide. So naturally what we expect is an exponential decay of the temperature starting at C naught, and the baseline temperature that we're going to reach is not unexpectedly the temperature of the lake, CL. Of course, such a physical model will never be completely accurate. For example, in truth, of course, the temperature of the lake is going to go up a bit. And in fact, these materials do not have a uniform temperature. For example, some parts of the iron will be hotter than others, and some parts of the lake will have a different temperature than other parts of the lake. But let's say for practical purposes, for at least many practical purposes, such a simple model will be sufficient. That example was about exponential decay. Let's now do an example about exponential growth. So let's get back to our lake, and suppose that on the other side of the lake, far away from our forge, we have a few water lilies growing in this very beautiful lake. Let's say that I'm interested in understanding the growth of the water lily population in the lake. And so I introduce a function, n of t. N of t is, for every time t, the number of water lilies in the lake. And in this case, t is measured in weeks. Now, what we know is that the function n of t, well, we know that it doubles every 4 weeks. So it's not difficult to find actually an explicit formula for that function, namely n of t is the same as n naught times 2 to the t over 4. Now here we've got an exponential with basis 2, and just for practice, let's rewrite this as an exponential with the Eulerian number. Now to do this, let's start with the function n of t, which is n naught times 2 to the t over 4. And certainly I can take the logarithm of 2 to the t over 4 and introduce the exponential again. This certainly doesn't change the value. Now, using properties of the logarithm, what I can do is I can pull out t over 4 from this logarithm, and so the entire function simplifies to n naught times the exponential of the logarithm of 2 over 4 times the time variable t. So what I can tell is that n prime of t, the derivative of n of t, must be the same as the logarithm of 2 over 4 times n naught of exponential of logarithm of 2 over 4 times t. And of course here I recognize that I've got the function n of t again. So what we see is that the number of volatilities n of t satisfies the following differential equation, namely n prime of t equal logarithm of 2 over 4 times n of t. That again can be described by a short graph, which I've outlined here. So we start at time n naught, and what we're going to see is an exponential growth of the number of volatilities in the lake. Well, that is an example of exponential growth where we already know the doubling time. In this case, it's for weeks. And from there, in this case, we have derived the differential equation. But sometimes we might not know the doubling time, but instead we know the differential equation. Now the next example is again about growth and decay, but this time within the social sciences. It's trending throughout a social network, and we're interested in the number of users of that app at any time t. So let u of t be the number of the users of the app at any time t, and suppose that at t equals 0, we've got the starting value of u naught users. So we know that u of 0 is equal u naught. Let's suppose that at every point in time, the rate of growth of that user base of that app is the following, namely 0.1 times the current number of users. So if we translate this into a differential equation, then we've got u prime of t equal 0.1 times u of t, and the initial condition is u0 equal u naught. Now it's fairly easy to find that the solution to that differential equation with that initial condition is the following, namely u of t equal u naught times exponential of 0.1 times t. Now that is very simple, but let's suppose we want to modify the model in order to capture certain effects that are not yet present. Now that is very simple, but let's suppose we want to modify the model in order to catch certain phenomena that are not yet part of our model, but which might be interesting in practice. So let us presume that t is measured in days. The rate of growth is still proportional to the number of users, but this time it is 0.1 times sine of pi of t to the square times the number of users. Now, where does the sine pi of t to the square come from? Well, let's suppose that the growth of the user base changes throughout the day. So, for example, let's say we are only in one country, and you might assume that at midnight the growth of the user base is close to 0 because everybody's sleeping, supposedly. But let's say that at noon, when everybody is awake and people are sharing their stuff on social networks and they're sharing with their friends, hey, I have this cool app here. So there's a peak for daytime, and there's a minimum that is close to 0 during nighttime. So maybe only at noon we're going to reach this maximum rate of 0.1. And that will be true, in fact, if t is equal 1/2, the half of the day, in this example here. And at t equal, whenever t is 0 or 1 or 2, so basically all the midnights, then this factor sine of pi of t to the square is going to be 0. Now, that is a practical justification of why such a model might make sense. If we write this down in terms of a differential equation, then what we get is u prime of t equal 0.1 times sine of pi of t to the square times u of t. Now, the differential equation can be solved with the formulas that we discovered in the previous video. Namely, the solution is u at time t is the same as u naught times exponential of 0.1 times the integral from 0 to t of sine of pi of s to the square ds. And at this point, I recommend you to actually verify that this follows from the formulas from the previous lecture. Now, what is the integral of the sine of pi times s to the square integrated from 0 to t? Well, there's an explicit formula for that, but actually we are not as much interested in this class in such an explicit formula. Instead, let's take a look at the graph of these two functions. So we have in the first model, we have our classical exponential growth. And here what we're going to have is actually a somewhat slower exponential growth. So what we can tell is that this exponent's integral from 0 to t of the sine to the square function is certainly going to be smaller than t. So what we can expect is that this function u of t is going to grow at a much lower pace than in our first model. In fact, what we expect somehow is that the second function is going to go through different phases that alternate. First, we have got an exponential phase, and the exponential growth is going to slow down as t approaches the midnight. Then it's going to go up again at the next noontime. And in fact, if we just plug this into a numerical solver and plot a graph of these two functions, then the result is going to look as follows. And on the one hand here on top, you've got the original exponential growth for our original model. And below here, we've got our growth function for our modified model. So first, maybe we start at midnight and there's not much activity. Then as t approaches the noontime, the activity goes up. Then it goes flat again. So at midnight, it's going to go up again, and so on and so on. Let's take a look at yet another variation of this growth model. And that leads us to what is known as logistic differential equation. So what we want to accommodate is the fact that this exponential growth can, of course, not go on indefinitely. So one reason is that we only have a finite number of people in the social network that could actually install the app. So let us say that P naught is the entire population number. And in the logistic differential equation, the growth of the user base is modeled as follows. Namely, the growth of the user base, u prime of t, is the same as alpha, which is some proportionality constant, times p naught minus u of t times ut. So how can we interpret this? Well, we again have that the rate of growth of the user base is proportional to the number of users we already have. So what has changed is that this factor here in front of u of t is now a function that actually depends on time. In fact, it depends also on the number of users. So to illustrate why we would come up with such a model, let's suppose that u of t is very small. It's much smaller than p naught. So in that case, the growth rate u prime of t is roughly the same as alpha times p naught times u of t. In that case, we expect u of t to have, again, almost the same as the exponential growth rate, for ut being very small. Now, let's suppose this exponential growth goes on and on. Then at some point, we will have a shortage of people who do not have yet the app. So if u of t is very large, then perhaps the only people who are left are the ones who are not interested in the app or who are maybe very difficult to convince to install the app. So in some sense, when u of t is very large in comparison to the entire population, then the only people who do not yet have installed the app are people who are very difficult to reach within the social network. So as u of t grows, at some point this factor p naught minus u of t is going to be very small. It's going to be very small and actually going to slow down the growth. Now, for illustrative purposes, let's introduce a new term for the number of people who are still available who do not yet have installed the app. Let's call this a of t. So a of t is p naught minus u of t. Now, if you're going to plot the number of users over time, then this is roughly going to look as here at the bottom of the screen. So at time t equals 0, we start with u naught. And first we're going to see the exponential growth, but then actually the growth factor dampens down, gets closer and closer to 0. And so the number of users is approaching the entire population number, but the growth is very, very, very slow. So as we're almost full, it's very hard to reach the rest of it. And conversely, the number of people who do not yet have installed the app starts at a naught, and then as u naught grows, it goes down correspondingly. The logistic differential equation was originally devised by a French guy who went by the name Pierre-François Verhulst. Let me write this down here. I'm pretty sure I got the French wrong. So his application actually was population models. So maybe you've got limited resources, and as you start with a population, maybe the population grows exponentially, and then as resources get shorter and shorter, the population growth slows down. And well, such phenomena also appear in various branches of biology, and in fact, of course, in sociology. I believe this is a very good point to get more and more familiar with systems of differential equations. So what we have here is two quantities, the number of users, u of t, and then we have the other quantity is the number of available people who have not yet installed the app, a of t. We can rewrite the initial system as follows, namely the growth rate u prime of t equals alpha times a of t, the number of available users at time t, and u of t, the number of users at time t. Now, our original expression for u prime of t can be rewritten as follows: u prime of t equal alpha times a of t, the number of available people in the social network, times the number of users in the social network u of t. I simply substituted P naught minus U of t with the definition A of t. And the number of available people in the social network has a derivative that can be described as follows, namely A prime of t equal, well, minus alpha times A of t times U of t, which of course is completely understandable, namely as the number of users goes up, the number of available people goes down by the very same amount. And both these two functions have two initial conditions, which we need to specify to describe the entire dynamics. Namely, U of 0 is equal U naught, and A of 0 is equal A naught. So we have rewritten the original differential equation, which only involves the function U of t, as a system of differential equations, where we now have this additional function A of t. That of course is a bit artificial, but we are going to take a look at an extended model, yet another modification of the model, where it is necessary to actually talk about a system of differential equations right from the get-go. So the modification for this model is as follows, namely we introduce a third category of the population. Namely, let us suppose that, okay, this app is trending throughout the social network, but then some people realize, okay, this is really a stupid app and actually I don't need it at all. And it's way too expensive and collects way too much information and takes up way too much memory. And so they uninstall the app and they vote to never use it again ever. So let us suppose that R of t is precisely that population at any time t. Let's say as the app goes online, we have at time t equals 0, the population is exactly 0. So the population of people who have uninstalled the app at time equal to 0 is exactly 0. So how does this population, the third population group, change? Now, we assume that we have users of this app and they uninstall the rate of people who remove this app, who get rid of this app at any time t, is proportional to the number of users again. So more precisely, the growth of that group R of t at any time t is beta times U of t, where beta is yet another proportionality constant. So if we write down the dynamics of these three population groups, U prime of t is alpha times A of t times U of t minus B of t. So the differential equation that describes U prime of t, it now involves two terms. On the one hand, we have alpha times AT times UT, which is the term associated with the growth. The term associated with the growth corresponding to this logistic differential equation. And then again, we have a constant decay, which slows down the growth or maybe makes it even negative. And that is modeled by this term minus beta times U of t. Now, still, A prime of t is just the same as before, namely minus alpha times A of t times U of t. And the third population group, the people who have removed the app, who have uninstalled the app, the growth of that group is R prime of t, which is, well, beta times U of t. And then again, we've got initial conditions. U at time t equals 0 is U naught. A at time t equals 0 is A naught. And we just said that the number of the third group, R at time equals 0, is just 0. Now, if you use the numerical solver to plot the evolution of that system of differential equations, what you get is a graph that probably looks very similar to what you see here on the screen. Of course, the details of the graph will depend very much on the parameters alpha and beta, and also the population sizes at the initial condition. So what we're going to see is that u of t is going to grow, just like before, with exponential growth, at least at the beginning. And a of t is going to deplete, just like before. So, but at some point, the growth from the available people who have not yet installed the app can no longer compensate the loss of people who are uninstalling the app. So at some point, u of t is going to go down again, and it's going to experience exponential decay. Whereas throughout the entire time, the number of people in the third group, r of t, see exponential growth. And essentially, as u of t goes down, again, this growth flattens down again. So in fact, r of t experiences something similar to the logistic differential equation. So lastly for this video, we will talk about a very famous system of ordinary differential equations, namely the so-called Lotka-Volterra models, or Lotka-Volterra differential equations. Now, the Lotka-Volterra differential equations describe the dynamics between two populations, one of which is called the prey, and the other one is called the predator. So the Lotka-Volterra model is named after two mathematicians. On the one hand, Lotka, who was an American mathematician who was interested in herbivores eating plants. And on the other hand, there was Volterra, an Italian mathematician, who was interested in the population dynamics of fish and fishermen. So just for the sake of illustration, let's say we have two populations, one of which is foxes and the other one is bunnies. The foxes are the predators, of course, and the bunnies are the prey. So we're interested again in how these populations develop over time. So we introduce two functions, x of t and y of t, which describes the population numbers of the prey and the predators, respectively. And the population dynamics of these two groups are determined by various factors. There's like procreation, there's infighting among the different populations, which leads to growth or decay of these populations. And then there's also interaction between these populations. For example, maybe the foxes are hunting the bunnies, and the more bunnies there are, the more the more resources the foxes have, and the more they can procreate. And on the other hand, of course, the more foxes there are, the less bunnies. So these dynamics can be described by the following model, or the following system of differential equations. Namely, on the one hand, x prime of t, the rate of change of the prey population, equal alpha times x of t minus beta times x of t times y of t. And the second equation is y prime of t, the change of the number of predators at any time t, is equal gamma times x of t times y of t minus delta y of t. In this scenario, alpha, beta, gamma, and delta are again some constants, which depends on the specific application. And of course, we have initial values. X at time t equals 0 is x naught, and we say that y at time t equals 0 is just y naught. Now, for the sake of illustration, we assume that alpha, beta, gamma, and delta are positive constants. But of course, if you just plug in negative values or zeros or whatever mix of these, you still get a differential equation, which is probably going to describe something. But for the sake of like predator-prey dynamics, we will stick to positive constants here. let's make a short review of what these two equations mean. So on the one hand, we have got x prime of t, and on the one hand, we have alpha times x of t, which of course models some sort of exponential growth. So in this model, we assume that the prey experiences exponential growth. So maybe it's just bunnies hopping around in the field, eating grass and procreating, and we assume that they have unlimited resources to procreate. They just experience exponential growth if it weren't for the predators. The second term models that the more predators there are and the more bunnies, the more will have a population loss of the bunnies. So in some sense, the number of bunnies being caught by foxes is proportional both to the number of foxes and the number of bunnies. On the other hand, okay, the rate of change of the predator population, y prime of t. So in the Logistic model, we assume that we have infighting among these populations, which lead to, well, a population decline, which is modeled by minus delta times y of t. So in some sense here we've got an exponential decay. If it weren't for the presence of bunnies. So the more bunnies there are and the more foxes, the more often a fox is going to catch a bunny. And in fact, that will influence the population growth. So we are going to expect that the more bunnies and more foxes, the more food there's for foxes and the more they're going to procreate. Which leads again then to a growth factor in the population. The dynamics of these predator-prey models is quite interesting, and there's much of mathematical theory about them. And so what you will see actually in practice is that these the solutions to these differential equations behavior. And one example here is given on the screen. So the blue curve here illustrates the prey population, and the red curve illustrates the predator population. So let us assume that x naught and y naught, the two initial conditions, are equal to 10. So in that context, probably it's reasonable to assume that we measure the population not in individuals, but maybe in thousands. Alpha, beta, gamma, and delta, let's say I have the following values: 1, 0.1, 0.1, and 0.4. So if you plug this into a numerical solver and have yourself displayed the solutions to these differential equations, then what you're going to see is that first the number of prey is going to go up as the number of predators is going to go down due to the exponential growth and exponential decays. But then as we have got many bunnies and many foxes, then suddenly the foxes have lots of prey they can feed on, and they grow again as the number of bunnies goes down. And as the numbers of bunnies has gone down, also the number of foxes goes down again. The predator population declines, and as the predator population declines, the number of bunnies goes up again. And that cycle just repeats over and over again. Well, such mathematical models, of course, particularly when we talk about population, are of course just models. These functions x of t and y of t will not assume discrete values, but continuous values, even though the populations that we describe are, of course, just measured in individuals. So it's not that we have like 0.12 foxes at some point, but the population then, the population models even though they're continuous, actually model the actual dynamics that you observe in ecological systems surprisingly well.